Hi, this is Miss Litton, and this is my 7th period review of Honors Bio Unit 3, and this is all about energy and enzymes. Say hi. Hi. Okay, so if we break this down, Chapter 6 on energy and enzymes, you want to review the laws of thermodynamics. Do you remember those two laws? What's the first law say? Energy cannot be created or destroyed. It can just change forms. And the second law says every time it does, you lose some as what? Heat. Yeah, so you lose some usable forms of energy. So how does this relate to entropy? Do you remember entropy? Aw, I'm in the middle of a review session. You just come by to say hi to me and to show me that super cute dress. I love it. I love it.
Birthday outfit.
I like it. Or do you need me for something?
No, just say hi.
How are you?
I'm good.
Okay, good. Okay. So entropy is the amount of what? What are we measuring? Thank you, sweetheart.
Disorganization.
Disorder. Yeah, the amount of disorder. And so our body systems, right, we do cellular respiration in order to fight disorder so we don't fall apart. And remember, we looked at those horrible pictures of those horrible kitchens, and some are really dirty, and we said they had high entropy and they don't have a lot of potential energy, but they're very stable. And then we looked at super clean, nice kitchens, and we said they have low entropy, right? But they're unstable because any little thing can upset that organization level, right? So we apply that to molecules, and more complex molecules like glucose have low entropy because they're super complex. You know, think about a Lego that you built that's all like intricate, but it has a lot of potential. It could just break down at any second, right, if you dropped it. But if all the Legos are on the floor spilled, it's not very useful, but they have less potential energy. Okay, so we talked about molecules, and we like to break down glucose in the process of breaking it down, the disorganization of the glucose allows us to build ATP in cellular respiration. Okay? And we'll hit that in the next chapter as well. We said, what is the role of ATP? ATP is our energy currency. We use it to facilitate a lot of our reactions in our body. If it's what kind of reaction? What kind of reactions require energy? There's this kind and this kind, just like there's this and this.
Endothermic. Yes.
Okay, that's just temperature. You're so close. Endergonic and exergonic. Okay, and we talked about coupling reactions, right? A reaction that requires energy is called what? Endergonic, and one that releases energy is exergonic. So if you do them at the same time, you couple those two reactions together, then one that releases energy, you can use that to do the endergonic reaction. Catabolic and anabolic. Which one, catabolic, is it ender or exergonic? Catabolic, what are we doing in catabolic? Breaking down. So if we break something down, you might have to invest a little bit of energy initially, but overall you're going to release energy in a catabolic reaction. An anabolic reaction, you're going to invest energy into it. Okay, look at me just for a minute. Okay, where are you at? Because you're not, guys, you're too loud over there. Where are you at? Because you're not here with me, and I know you're trying to bear down and just get through all your loads of business you have to do as you get ready for finals. But did I move too quickly through 1 and 2? I want it to be useful to you. Do you have any questions about 1 and 2 that's on the board?
Not really.
I'm going to No questions on 1 and 2? Okay, so let's move on to number 3. Okay, team, I'm going to ask you to leave if you can't be quiet because they're getting ready for their final. Okay, how do enzymes work and how are they regulated? So if I asked you that right off the back, how do enzymes work? What are the things that come to your mind when I ask that question? What do enzymes do for us?
Breaking down stuff? Like
they might.
They accelerate reactions.
They accelerate the rate of reactions. How do they do that?
By reducing the rate of, or the
Energy of activation.
yeah,
Energy of activation. They lower the energy of activation. And how do they do that? By binding with the substrate. Where do they bind with the substrate? There's a specific location at the enzyme's
Site.
what?
Site.
Active site. And by controlling the state of the active site, we can control an enzyme's functionality, right? If there, we talked about different types of competition. Do you remember what those are?
yeah. There's in like non-competitive competition.
Yes, non-competitive and
Inhibiting.
non-competitive inhibition and competitive inhibition, right? So if you bind to the if you're a substance that binds to the active site, you're competing with the substrate for that active site, right? And so as a result, the substrate can't bind to it, so you can't facilitate that reaction. In a non-competitive inhibitor, you're binding to a secondary site, an allosteric site, which then changes the active site. Okay? So that's the part about how they're regulated. And remember, we also talked about how sometimes you need vitamins to make, to activate, like as a coenzyme, to make that enzyme function. Okay, think about 3. Look at your notes you just took as you're bearing down. What questions might you have about 3? Ask the person next to you, are you okay on this? Or there's some more questions you have just on number 3. Okay, so when we think about how do enzymes work, they work by they make a reaction go faster by lowering the energy of activation to make it more likely for that reaction to occur. The types of reactions we have, some may require energy, those are called what? Endergonic. Some release energy, that's called exergonic. When we talk about energy, we're trying to fight entropy. We're trying to fight disorder in our bodies. And the energy currency we use to fight disorder is called ATP, adenosine triphosphate. All right, and we can couple the breaking down of ATP, the catabolism of ATP, with an anabolic reaction. We can couple those two together. On number 4, what is the difference between being oxidized and reduced, and how does that happen? Those 2 words come up a lot in cellular respiration and photosynthesis. Okay, which one are you gaining energy, in oxidized or reduced?
Reduce.
Reduced, you gain energy. How can you gain energy when you are reduced? What would happen?
Well, you're gaining negative electrons.
Okay, you could gain electrons. Oops, sorry.
Right?
You could gain electrons. What else could you do?
I mean, it's
Gain hydrogen ions or energy. Those are all talking about when something is reduced. When something is reduced. Okay, it gains energy, could do it by gaining electrons, it could be gaining hydrogen, or what else could you do? Take away oxygen. Remember that? Okay? If you remove oxygen, you can become reduced, and the reason is when oxygen is with you, it takes away your electrons. It has a higher electronegativity, and it pulls the energy, the electrons away. So if you get rid of oxygen, he can't do that. And it's the opposite of that for oxidized. And then these 2 reactions, they're always coupled. If you're oxidizing something, then something else is getting what? Reduced. Okay. Questions or concerns on that topic? Anything of these 4 that you want me to go over a little bit more? What was entropy again?
level of
Disorganization.
Disorder. Okay, what was the first law of thermodynamics?
Energy cannot be created or destroyed.
Okay, so it can't be created, destroyed, and then what was the second law?
When
Energy
transferring energy
is
between
given
organisms.
off its heat.
Yeah, so when energy changes hands, you lose some as heat, usable energy. Okay, exergonic releases Energy and endergonic,
Takes in energy.
yep, requires energy. Catabolism, build or break?
Break.
Break. Anabolism is?
Build.
Build. Okay, and different color, green. How do enzymes work? They lower what?
The energy of activation.
Yep, lower the E sub A. Okay, we don't have to race, we just want to make sure everybody gets a chance to think. What did we say about ATP? It's our energy what? Currency. What are some of the roles of ATP? They can be used for what?
ATP Cellular respiration.
Okay, so we get it as a result of cellular respiration, but remember we said, what are the different kinds of work you could do? You could do transport work, right? What else could you do?
I know you do, but it's at 8:30 in the morning.
Okay, no problem. I'll do it before I leave. This is one of those days
No,
where I
I know.
teach 0, 1, 3,
Okay.
5.
And it's the 504 one, not, if I gave you the SST, it's not.
Oh, I tossed the first one you gave me and I'm just gonna do the second one. Okay. I'll bring it over, put it on your desk.
All right, that's fine, I just knew it was.
Okay.
Fine.
Okay, transport work. Do you remember the other kind of work? Chemical work. Transport work, you can use ATP to help you do like active transport across the cell membrane. Remember that? The different ways that ATP can be used. That would be like active transport requires ATP. Okay, chemical work, we could be doing like building. And there was mechanical work, like muscles contracting, cilia moving. Okay, any questions on that? Okay, so then our next topic, we can kind of put these together, cellular respiration and photosynthesis, because they're linked. Okay, so it said write the equation for cellular respiration, identify what gets oxidized, reduced, and then name each major step, where it occurs and its purpose. Repeat with photosynthesis. So what is the equation for cellular respiration? C6, H12, O6 plus 6O2 goes to what?
6 CO2.
6 CO2 plus 6 water plus
Energy.
energy. Okay? Plus energy. What is the form of that energy?
ATP.
ATP. Okay? If we do photosynthesis, if we go this direction, this way is photosynthesis, this way is cellular respiration, then that energy when we go this way isn't from the what? The sun. Okay? And we know that, let's see, black, I guess. We know that when we do cellular respiration, the glucose is going to become CO2 and the oxygen is going to become water, right? So the O2 gets reduced. The O2 gets reduced into water and the CO2 gets oxidized into CO2. And if we're doing photosynthesis, the CO2 is going to become what? What's the CO2 going to become? Photosynthesis. What does the CO2
Oxygen.
become?
Oxygen.
No, it does not become oxygen.
Sugar.
What? Glucose. Yeah. Right? Okay, it gets reduced into glucose. When does it happen? In the light independent reaction, perhaps? Another name for that is the dark reaction. Another name for that is the Calvin cycle. Right? And the water gets what? Water gets oxidized. When does that happen? During the light reaction, the light dependent reaction, remember? What are you going to do to water? Break it in half? I'm just going to assume you're really tired. Are you just really tired? I'm getting 0 responses from you. Okay, so you're probably going to want to review that and review your different steps. Okay, for cellular respiration, your big things you're going to need to review, or here we can do this. No, I don't know if that'll help you. cellular respiration, if you do it always starts with what for cellular respiration? What's the first step? Glycolysis, right? Where does glycolysis occur? In the cytoplasm. Good. What do you start out with? Glucose, right? That's your C6H12O6, right? What are you going to break it down into?
2 private acids.
Yeah, 2 C3s, which are pyruvic acid. How many steps?
10.
Yeah, so this is 10 steps, and along the way you reduce some NAD, and you make what? 2 is what you net out, right? Okay, now if you have oxygen, if you go this way, you're with O2, you're going to move into the mitochondria. What's next? Transition.
Prep.
Yes. So you're going to change the pyruvic acid into 2-acetyl-CoA, which is then going to go through your Krebs cycle. Good Lord. Okay, so in the process you will kick off, you will do the Krebs cycle 2 times, so a total of 6 NAD reduced if you do this 2 times. And you're going to get 2 FAD reduced and 2 ATP. Remember, 2 plus 4 is 6, do the big, get 5, do the big, get 4, right? That whole thing. Then these right here, these are going to go to your electron transport chain. Oof. Electron transport chain, and you're going to make even more what? ATP. If you don't have any oxygen, if there's no oxygen, you're going to do what else? Fermentation. And you're going to take your NAD that is reduced and you're going to oxidize it so it can be used again in glycolysis. And then you have 2 choices. You're going to make alcohol and CO2 if you are a plant. And you're going to make what? Lactic acid if you're an animal. You okay?
Can you leave that there for a second?
Sure. Okay, so those are the steps of glycolysis. So now, you want to do photosynthesis? Okay. So photosynthesis is going to occur where?
Chloroplast.
In the chloroplast. Good. Okay. So chloroplast. Remember what? Oh, sorry. So sorry. Chloroplast. Double membrane, and remember it has. You want to just kind of keep track of where things are. What are those green things called?
Thylakoid membrane.
Yep. Thylakoid. And what happens there? A light reactions. Okay. And then what's this area right here? Stroma. And these are the light independent reactions. This is your Calvin cycle. Remember 3C5 plus 3C1 makes 3C6 breakdown to 6C3. Okay, use some ATP, use some reduced NADP. Yes, you got all that. So what was the 3C5? What was that? RUBP. Okay, and that's the thing that hooks up with CO2. So this is the C5, and this is 3C5 plus 3C1 makes what? 3C6 breaks down to 6C3. Use some ATP, use some reduced NADP on your 6C. Right, you're right, 6C3. Take 1 away, okay? Yeah, PJL or G3P. And you're left with 5C3. Use some ATP to build 3C5 plus 3C1, right? Okay, so where did this ATP right here come from that we need, and where did this reduced NADP come from that we need?
Photosystems, right?
Yeah, from the light reactions, right? In the light reactions, you start with water, right? And you break it in half, and this is when we said, what do you get? Oxygen and what else? Electrons. Those get excited in photosystem 2, and you make some ATP. And then it gets excited again by the sun, and you form some reduced NADP. So this, from the light reactions, this is what you have to do the light independent reactions. Yes, no, maybe so? Processing? Okay. So then the last thing on here talked about what is photorespiration. That's when RUBP hooks up with who? O2. Yeah, that's bad. How do you avoid it? CAM plants or PEP, okay, which are C4 plants. And they hang on to CO2 either at night or in a different cell. And then they release the CO2 only to the RUBP. They don't ever hook up with oxygen. So that's using PEP. And then you don't have to worry about that. All right, you okay? Questions you want to ask me? Yes.
Yes, I'm not really getting the whole the oxidation and reduced part of the in the equation.
Okay. So if you look here, here is C6H12O6, right? Then it becomes just CO2. What's missing?
Well,
This one has carbon, hydrogen, oxygen. This one has what? Carbon and oxygen. So what did it lose?
Hydrogen.
Hydrogen. So therefore glucose got oxidized because it lost hydrogen. Where did that hydrogen go to? Here's oxygen, here's hydrogen and oxygen. Where did that oxygen go? This hydrogen right here, in essence, this hydrogen right here is now here.
So it's giving its electrons to
Yes.
oxygen, so that's getting used, right?
Right, exactly.
Okay.
And vice versa.
All right.
Okay, other questions or concerns about that? Anything else you want to ask me about those? Okay, way to power play it. Good job, you guys. I'm super proud of you. Have a piece of toast if you're up really late, but don't be up really late. Make good choices.